Hey, this is great, Will. One question I have, given the scale of how SKA is built out, and this is a great backdrop for the question. What is the overall team harness in terms of either simulation or emulation to help kind of test some of this out before it gets deployed at this scale?
So there's several different stages that we go through. So we have the prototype system integration lab, which is in Canada. That sits there, and it just allows engineers to come in and play with the correlator and integrate other systems with it. So currently we're integrating some of the beam-forming stuff for doing pulsar search. So they've sent over a server with some GPUs in it, and we can then generate some data and send it to them to make sure that integrates nicely. Next stage is deployment to the verification guys in South Africa. So they have another lab where they have another instance of the correlator, and then they can do tests. They can integrate it with the dish data. They've got sky simulators and stuff to generate signals, and they can connect that to the science data processor and start integrating there. And then we move out into the actual deployment. Our team does a lot of work simulating all of our firmware. We have a lot of unit tests, and then we do a larger simulation to bring all of our IP blocks together. On the software side, we're putting together an emulation simulator type thing that takes the hardware out and replaces the hardware's API with a sort of a REST type interface, so that we can scale out that emulation of all of the hardware and then test the software that needs to control it at scale. So that's a new thing that we're attempting to do, just to try and get away from having to have too much hardware and being able to have lots of teams be able to work on the correlator software without having the hardware underneath to back it up. Hardware is very expensive.
Yeah. That's what I figured. Okay, thanks.
No pun intended. Yes, I saw another hand somewhere for another question. Yes, here in the front, Patricia.
Can you talk a little bit about the data bottleneck? You mentioned some high frequencies of transmitting data.
Yep.
But I was wondering how much of that data is can be processed on the sensor. How much is it going outside? What are the computation capabilities to recover all the nice images you were showing? Are you looking into ML and AI for that? Yeah, so a little bit on the what do you do with the data when you get it? Can you do it distributed?
Okay, that's a very big question. So we get 20 terabit per second from the dishes. It's basically comes in at line rate. It's like 98 gigabits per second. The correlator needs to process that all in real time, because we just can't store 20 terabits per second for 24 hours a day, 7 days a week, 365 days a year.
As someone thought at the beginning that it was a good idea. Remember, I mean, if you walk out there, you will see the signs of our original presentation, 2013, 14.
Yep.
They expected to process 157 terabytes per second and create science data centers in countries. And one would be here in Canterbury to process that. I mean, those are scientists who think without a managerial hat.
The scientists demand a lot. So the correlator mashes all of that data together. It actually gets bigger by n squared, where n is the number of receptors. And then we do a lot of integration, so averaging to bring the data rate down. That gets shipped to the science data processor in Kamp. That's a 25 petaflop machine, I think. And they take the visibilities, so the fringes, and they grid them, so they put them on a two-dimensional grid based on where the receptor is at any point in time. And then they do an inverse Fourier transform of those gridded visibilities, and that gives you your image, a very noisy image. So they do this cleaning algorithm that goes round and round in circles, trying to estimate what the missing data is. And then after they've got an image, that image cube, so it's a two-dimensional image, but for 65,000 frequencies. They ship that off to regional data centers around the world, where the scientists then get their hands on it. And then the scientists can do what they like. They can apply AI to it, machine learning, machine vision. I know they've had a lot of success recently with categorizing galaxies that they see in images. So normally you get a graduate student to go through and categorize them, right, one at a time, but with 600,000 galaxies in a small patch of sky, that's not going to work for graduate students. They have to apply AI. So I think there'll be some very interesting science that comes out based on AI results of categorizations and looking at the distribution of matter in the universe and those fun things.
Before I give the word to Jess, how much data do you lose?
How much data do we lose?
Yeah.
It is an unknown yet. That RFI that I showed earlier, that's a big problem. That's a big thing that we need to mitigate with the telescope. So we'll have satellites going overhead. All of those Starlink satellites, even if they turn them off, they're very noisy. They've still got.
But even
watts.
with the data that you collect, you can quantify how much do you lose in the process until it gets from the capture into the hands of the scientist? 5%?
I don't know the answer.
Okay,
but
that's okay.
Yeah, excising all of that RFI will have a big effect. And we need to give the scientists the best quality images that we can. Yeah.
Jess.
Yeah, thanks, Will. Always good to see the updates to the Mega Science project, and as you say, there's often various types of delays, engineering, political. I think you mentioned a few other bits and pieces. I'm curious, how do you think it's going now that you've sort of got these two bits of the instrument that are kind of on slightly different timeframes now? Is there kind of opportunities to be, seeing what SKA low is doing and kind of bring that into SKA mid? How's that working for you guys at the moment?
Yeah, we look a little bit, and there's some communication. Very early in the project, I was on both correlators working from AUT, and that helped a lot. So we tried to keep that communication going. Yeah, they're about 6 months ahead of us, so it's not a lot of time to react. But the low telescope moved to a COTS solution with Xilinx FPGAs quite a while ago, a couple of years ago. So we've sort of followed suit with that. So there are learnings between the two telescopes.
I guess my other question is with one of these really long baseline science projects that's going on. You mentioned things like the radio interference from Starlink. This wasn't something that was around in 2018. Have you got some other examples of things where you sort of had quite a radical change in direction from that initial vision, or what's been the biggest one in your opinion?
The RFI has always been a concern. It's just got worse and worse and worse. Other changes, I don't know. I'm just an engineer. I get told what to do and I do it. Technology has changed, so it's taken time. So now we get this technology refresh opportunity, which adds quite a bit of work. But the algorithms that were designed back in 2016, 2015, those are still the same algorithms that we're using.
So you're still seeing the kind of the bottlenecks in the same places you expected? They're not kind of moving around with the changes in technology at all?
No, not really. So the increase in Ethernet bandwidth has been good. We had a we had our own solution for moving data between FPGAs on 25 gigabit per second optical links. So we had a huge optical mesh that sat in the back end. So now we've moved to using switches between all of our FPGAs. So that's been, I wonder how well it's going to work, because now we've got a lot of switches to also configure and get that right. But it does give us the opportunity to move data to different parts of our system and work on it differently.
So it sounds like a huge Ansible issue for managing all of that.
Yeah.
Well, I want to add a little bit on what Jess, asking him, but also what Andrew said. I mean, I spent nearly a decade with the SKA just trying to put things together. So it's a managerial question. What's your relation today with the vendors? Because I remember in 2010, 2011, we were asking a number of things, and the vendors say, why are you asking that? I mean, we were talking exascale. I mean, Jack Dongara was paying attention to our questions just because we were asking a number of things that they weren't in the roadmap. I'm not saying that any vendor changed the roadmap for the SKA, but it has been, I mean, you just speak about commercial off-the-shelf stuff these days. So how is the vendor relation these days, and how is a vendor paying attention to this project? Because at the end of the day, you are not making money out of this, or it's a feeling good project perhaps, but what's the situation these days?
I've been working with Intel and, well, now Altera again, and they're reasonably responsive. We've got a couple of vendors for IP, and they also work pretty hard for us to get things right. Early in the project, we had FAEs who were very excited because they thought they were going to get a big paycheck, but they've since retired, I think. So the FAE side has sort of fallen off a little bit. We don't get quite the support we used to, but the technology is also maturing, so we don't need as much support.
What's your view, Andrew?
Yeah, I think it ebbs and flows a little bit. I mean, there's certainly always, and every company is going to be different. And by the way, in situations like this, most companies we don't like to be thought of as vendors. Like, if we're going to be part of this, then we want to be a partner, right? We want to be a collaborator. So even that tone kind of matters. And so there's an outreach part that is just like, well, of course, if we can be a part of this and support it, because it's for the greater good, we always want to be doing a number of those projects and be involved in that. And at least for our company, that's where my team actually, we're kind of the front for a lot of that. So I think you'll always find most responsible companies that want to do good and be a part of it. Now, as I look at this and kind of get re-engaged on it a little bit, because I haven't thought about the project in a while, from a networking side, we do a lot of wireless. There's a lot to be learned here through, a lot of the interference and the tracking that you do. So, there would be a reason, I think, even for us to, have an extended interest, just because of the problems that you're, encroaching upon and trying to solve.
Ben, you had the mic. Oh,
sorry.
Anna.
Really fast. I know Oak Ridge was working with you guys for compression on the edge. Is this something you're still doing?
Not in the CSP side of things.
I mean, the United States is not officially involved in the SKA for a number of reasons which are beyond this conference.
Yeah. The United States have their own telescope in the works, the next generation VLA.
That has been for the past 15 years?
Yeah. Similar timescales to the SKA. And I think it's going to be a complementary instrument.
I mean, scientists work alongside each other everywhere in any topic. So I walk through SCE and mention SKA, and it's a conversation starter. But Ben?
In my former life, before I went to Oak Ridge, I worked at Lockheed, and anything space goes immediately to security, clearance, blah, 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 all that stuff. Do you have any issues or challenges that you have to work through when you're talking about collecting images of space? From a computing standpoint, not getting into the security implications, but are there challenges that you have to deal with because you're looking in that area?
Looking into space?
Just looking up into space.
Not that I'm aware of. Anything space related does get difficult. Fortunately, we're on the ground. It's one of those tick boxes on your professional indemnity insurance that you have to say, I'm working in space, or no, I'm not, really not.
Jason.
So what prompted the selection of the Agilex 7? I imagine that you needed the HBM for buffering and the sufficient networking to get all the data off chip as quick as you could.
So Agilex 7 is the next generation after the Stratix 10. It has the same architecture underneath, so Hyperflex architecture. So that makes transferring our designs from Stratix 10 to Agilex 7 very easy. If we were to go to the equivalent Xilinx chip, then that change would be a little bit more difficult. Not impossible, but more difficult. The Agilex 7 with HBM in it is amazing. So much bandwidth that you can start doing some interesting things. And the chip's just that much bigger again than the Stratix 10. We can process 3 antennas in the one chip instead of one. So it's, Agilex 7 chosen because it's the next generation from Altera, and it's easy for us to move to.
Cool. So before I give the microphone or ask you to thank Will, I just want to make a reflection. I mean, we had a team. I mean, Will wasn't just a extremely talented guy. We have an extremely talented team working here, and I always felt guilty that I wasn't able to convince Minister 4 or Minister 5 to continue the time within the SKA, because I mean, you learn how to love people that you hate and vice versa in terms of strategy and politics, but it's an open question to this room. I mean, for us it was a once-in-a-lifetime opportunity for a country like New Zealand to be leading certain activities. And we just failed to convince the funding bodies. And I think that it was about 30 million New Zealand dollars for the entire life cycle, which is the money that they spent on the methane sat project without any consideration. So I'm ranting in a nearly personal way, but the open question is, what we could have done better in order to keep going this. And this happens all over the world. I mean, I'm sure that again, funding for NSF or whatever, you just add a few zeros, but it's the same situation. What should we do to convince certain politicians or funding bodies that mega science comes with a lot of benefits for everyone else? And I've seen this in South Africa. In South Africa, they have doing just a wonderful work because they take it as a matter of national pride, not just national security. And trust me, we have a better general economic situation than South Africa. However, they are still into that. So that's an open question to discuss later. Join me in saying thank you to Will Kamp.